Dear students, we are going to continue our discussion on mole concept in this chapter as well, which is concept of equivalent. When we think about concept of equivalent, the first question that arises in our mind is, what is an equivalent? One equivalent of a substance in a reaction can be defined as the amount of substance which reacts with or liberates 1 mole of electron in a redox reaction or 1 mole of hydrogen ions or hydroxyl ions in an acid-base reaction. In a chemical reaction, one equivalent of a reactant always reacts with one equivalent of another reactant. The equivalent mass of a substance can be defined as the molar mass of the substance divided by the number of the equivalents of the substance dissolved in 1 liter of the solution. We have already discussed molar mass in the chapter Introduction to Mole Concept. Now, if we know the equivalent mass of a substance, we can calculate the number of equivalents of the substance, which will be equal to mass of the substance divided by equivalent mass. Now, the equivalent mass of a substance is not fixed like its molar mass. Equivalent mass of the same substance can be different in different reactions. For example, 1 mole of iron can react with either 2 or 3 moles of hydroxyl ions depending upon its oxidation state. Therefore, the equivalent mass of a substance is always defined in context of a specific reaction. Let us consider an example of how the equivalent mass of a substance becomes different with different reactions. Potassium permanganate, KMnO4, acts as an oxidizing agent in different manners depending upon the medium of the reaction. In acidic medium, the reaction can be written as MnO4 minus plus 8H plus 5 electrons will give Mn2 plus 4 H2O. As you can see that 1 mole of potassium permanganate reacts with 5 moles of electrons. So, the equivalent mass of potassium permanganate will be equal to its molar mass divided by 5. In weakly acidic or neutral or slightly alkaline medium, the reaction can be written as MnO4 minus plus 4H plus 3 electrons will give MnO2 plus 2 H2O. As we can see that 1 mole of potassium permanganate reacts with 3 moles of electrons. So, its equivalent mass will be equal to its molar mass divided by 3. Similarly, in alkaline medium, the reaction can be written as MnO4 minus plus electron will give MnO4 2 minus. Since 1 mole of potassium permanganate is reacting with 1 electron, its equivalent mass will be equal to its molar mass in this case. Let's take a few examples. We have to determine the equivalent mass of the highlighted reactant in each reaction. In the first reaction, we have to find the equivalent mass of phosphoric acid. In this reaction, we can see that 1 mole of phosphoric acid liberates 2 moles of hydrogen ions. Hence, its equivalent mass will be its molar mass divided by 2. Since its molar mass is 98, its equivalent mass will be 98 divided by 2, that is 49 gram per equivalent. We discussed in the chapter Introduction to Mole Concept how to determine the molar mass of a substance. I hope you remember. For a reminder, the molar mass of phosphoric acid will be 3 into atomic mass of hydrogen plus atomic mass of phosphorus plus 4 into atomic mass of oxygen. In the next reaction, we have to determine the equivalent mass of copper sulfate. As we can see in the reaction, 2 moles of copper sulfate liberated 2 moles of iodide. So 1 mole will liberate 1 mole of iodide or 1 mole of electrons. Therefore, in this case, the equivalent mass will be equal to its molar mass, that is 159.6. In the next reaction, again we have to find the equivalent mass of phosphoric acid but in a different reaction. So 1 mole of phosphoric acid reacts with 3 moles of hydroxyl ions. Hence, its equivalent mass will be its molar mass, that is 98 divided by 3, that is 32.66 gram equivalent. As we discussed recently, that the equivalent mass of a single substance can be different in two reactions, as can be seen. The equivalent mass of phosphoric acid in this reaction is 49, whereas in this reaction it's 32.66. In the last reaction, we have to determine the equivalent mass of oxygen. 1 mole of oxygen is equivalent to 2 moles of H2 molecules or 4 moles of hydrogen atoms. So we can say that the equivalent mass of oxygen in this reaction will be its molar mass divided by 4, that is 8 gram equivalent. Let's take another example. We have to find out how many equivalents does 33.6 liter of hydrogen and chlorine gas contain at NTP, that is normal temperature and pressure. Now we have already discussed in the chapter Introduction to Mole concept that 1 mole of any gas at NTP will occupy 22.4 liter volume. So if the volume is 22.4 liter, the number of moles is 1. Now if the volume is 33.6 liter, the number of moles is 1 divided by 22.4 into 33.6, that is equal to 1.5 moles. Now we know that 1 mole of H2 is equal to 2 equivalents of H2. So 1.5 mole of H2 will be equal to 1.5 into 2 is equal to 3 equivalents. Similarly, 1 mole of Cl2, that is chlorine gas, is equal to 2 equivalents of Cl2. So 1.5 moles of Cl2 will be equal to 2 into 1.5, that is again equal to 3 equivalents. So hydrogen and chlorine gas at NTP will contain 3 equivalents each. The concentration of a solution can also be expressed in terms of normality. Normality can be defined as the amount of solute in equivalents dissolved in 1 liter of the solution. It is symbolized by capital N. Its unit is equivalents per liter. We note that the volume of a solution changes with temperature. Since normality depends on the volume of the solution, it is also temperature dependent. Now we know that normality, that is N, is equal to the amount of solute in terms of equivalents divided by the volume of the solution in liters. Therefore, on rearranging this equation, we can also write that the number of equivalents is equal to normality into volume, that is N into V. In volumetric titrations at equivalent point, we know that the number of equivalents of one reactant is equal to the number of equivalents of the second reactant. Therefore, we can also write N1V1 is equal to N2V2. This expression is quite useful in volumetric titrations. Titration is a method of quantitative analysis which is used to determine the unknown concentration of a known reactant. A reagent called the titrant of known concentration and volume is used to react with a solution of the analyte whose concentration is not known. The analyte can also be called titrant. Using a calibrated burette, the exact amount of titrant that has been consumed till the end point is reached. The end point is the point at which the titration is complete. It is determined with the help of an indicator. This is ideally the same volume as the equivalence point. The number of equivalents of titrant is equal to the number of equivalents of analyte or titrant. Hence, in volumetric titrations, we use the expression N1V1 equals N2V2 for the equality of substances being titrated at the equivalence point, where N is the normality and V is the volume. Let's solve a numerical. A 1 gram of hydrogen peroxide solution containing X% hydrogen peroxide by mass requires X cubic centimeter of a potassium permanganate solution for complete oxidation under acidic condition. We have to calculate the normality of the potassium permanganate solution. Now the equation for potassium permanganate in acidic medium can be written as MnO4 minus plus 8H plus 5 electrons gives Mn2 plus 4H2, and for hydrogen peroxide H2O2 gives O2 plus 2H plus 2 electrons. Now from this equation you can see that 1 mole of hydrogen peroxide liberates 2 moles of electrons. So equivalent mass of hydrogen peroxide can be written as its molar mass divided by 2. Since its molar mass is 34, its equivalent mass will be 17 gram per equivalent. Now for X% hydrogen peroxide by mass, the mass of hydrogen peroxide in the given 1 gram sample will be equal to X upon 100 into 1 gram, that is X upon 100 gram. The number of equivalents present in the sample will be equal to its mass upon equivalent mass. So X upon 100 upon 70, that is X upon 1700 equivalents. Let us mark this equation as equation A. Now this will be equal to the equivalence of potassium permanganate consumed in the reaction. Now assuming that the normality of potassium permanganate solution be N, we can write that the number of equivalents of potassium permanganate in the sample will be equal to its normality into volume, that is N into X upon 1000 equivalents. Let's mark this equation as equation B. Now equating the values of equivalents of hydrogen peroxide and potassium permanganate, we obtain X upon 1700 equivalents is equal to X upon 1000 into N equivalents. On solving this equation, we get N is equal to 10 by 17 equivalents per liter, which is equal to 0.588 equivalents per liter. This is our final answer. Our next subtopic is oxidation number. Oxidation number can be defined as the charge that a species would have if all the electron donors were removed along with their electron pairs they were sharing with that species. There are certain rules for determining the oxidation number of a species. For example, a free element, whether it exists in monoatomic or polyatomic form, for example, let's say P4 or S8, is assigned an oxidation number of 0. A free monoatomic ion is assigned an oxidation number equal to the charge it carries. For example, the oxidation number of sodium plus ion is +1. Similarly, for fluoride minus ion, F minus, it is -1. The total algebraic sum of oxidation numbers of atoms in a chemical compound or ion is equal to the total charge on the species. Compounds are neutral, therefore the algebraic sum in their case is 0.